Hi guys. Okay, so today we're going to learn how to use that document that I sent to your TI calculators, your TI-Nspire. We're going to learn how to use the Riemann sums program or document. It's not really a program. So before we do that, let's start with a simple function. F of x is 2x minus x squared on the closed interval from 0 to 2. And we want to estimate the area under the curve using an LRAM sub 4, RRAM 4, MRAM 4, and Trap 4, which means we want 4 subintervals. So we're looking for n to be 4. We also need to know our delta x. Our interval goes from 0 to 2, which means we do b minus a, so 2 minus 0, over the number of subintervals, which is 4. So our delta x is 1/2, which means when we separate this from 0 to 2, we're going to separate it at 0, 1/2, 1, 3/2, and 2. The length of each subinterval will be 1/2. Now for the LRAM, I'm going to factor out the 1/2, okay? And then for the LRAM, we use the left endpoint. So the first subinterval is from 0 to 1/2. We're going to substitute 0 into the function. And then from 1/2 to 1, we're going to substitute 1/2 into the function to find the height. From 1 to 3/2, we're going to substitute 1 into the function to find the height. And then from 3/2 to 2, the one on the left is the 3/2. We'll substitute that into the function. Now before we go anywhere, let's do some function values here. If f of x is 2x minus x squared, this way we don't have to compute it over and over again. F of 0 is 0 minus 0, which is 0. F of 1/2 is 2 times 1/2 minus 1/2 squared. So we're going to have 1 minus 1/4, which is 3/4. F of 1 is going to be 2 times 1, which is 2, minus 1 squared is 1, which gives us 1. F of 3/2 is going to be 2 times 3/2, which is 3, minus 3/2 squared, which is 9/4. So that's really 12/4 minus 9/4, and that's going to give us 3/4. And then f of 2 times 2 is 4, minus 2 squared is 4, is 0. So this will be like our little toolbox over here on the corner. Okay, so now back to my LRAM, I have 1/2, and we said that f of 0 is 0, plus f of 1/2 is 3/4, plus f of 1 is 1, plus f of 3/2 was 3/4. All right, and if we do that addition, we're going to have 1/2. Now 3/4 plus 3/4 is 6/4. 0 plus 1 is 1, but I want to write that 1 with the denominator of 4, so it's 4 over 4. And then 6/4 plus 4/4 is 10/4. When we multiply that by 1/2, we're going to get 5/4. And if you prefer decimals, 1.25. There we go. Now we're going to do the RRAM. Each delta x is the same, it's 1/2, so I'm going to factor it out. Now for the RRAM, we use the right endpoint. So from 0 to 1/2, 1/2 is on the right. We're going to substitute that into the function. From 1/2 to 1, 1 is on the right, so we substitute that in to find the height. From 1 to 3/2, 3/2 is on the right, so we substitute that into the function to find the height. And from 3/2 to 2, 2 is on the right, so we substitute that into the function to find the height. So now we have 1/2 times. We said f of 1/2 is 3/4, plus f of 1 is 1, plus f of 3/2 is 3/4, plus f of 2 is 0. Notice that's the exact same sum just in a different order that we had for the LRAM. So we're going to wind up with 5/4 or 1.25 yet again. Now the MRAM. Again, our delta x is still 1/2. But this time we use the midpoint of the interval. So midpoint between 0 and 1/2 is 1/4, plus midpoint between 1/2 and 1 is 3/4, plus midpoint between 1 and 3/2 is 5/4. We're plugging these into the function. Plus the midpoint between 3/2 and 2 would be 7/4. And it's okay if you want to use the decimals, that's fine. Let's go through. If you want to use your calculator to compute, let's see, we're going to do 2 times 1/4 minus 1/4 squared. We're going to get 7 over 16 plus f of 3/4. We're going to do 2 times 3/4 minus 3/4 squared. We're going to get 15 over 16. F of 5/4. We're going to do 2 times 5/4 minus 5/4 squared. we're going to get another 15 over 16. F of 7/4, we're going to do 2 times 7/4 minus 7/4 squared. We're going to get a 7 over 16. So that's going to give us 1/2 times, add that up, 30 and 14, 44 over 16 times 1/2 is 22 over 16. Reduce that to 11/8, which is 1.375. Okay, now we have one more to do. We need to do our trapezoid. So our trapezoid, remember, since all the delta x's are the same, we can do 1/2 times our height, which is still 1/2 because our 1/2, our height is our delta x. Then we use the first subinterval at 0 ones, all the ones in the middle twice, so it's 2 times f of 1/2 plus f of 1 plus f of 3/2. And then we only use the right endpoint once. And then we close this up. So 1/2 times 1/2 is 1/4. F of 0 was 0, plus 2 times f of 1/2 was 3/4. F of 1 was 1. F of 3/2 was 3/4, plus f of 2 is 0. So we are looking at here again a 1/4 times 2 times 3/4, and 3/4 is 6/4 plus 1, which is 4/4. So we have 1/2 times 10/4, which is 5/4, which is the 1.25 yet again, which we should also have known because remember the trapezoid is the LRAM plus the RRAM divided by 2, and since the LRAM and the RRAM were the same, then the trapezoid would also be the same. Now the question is, how can we improve our approximation for the area under the curve? By using these same 4 methods. And we've discussed this before about using more rectangles or even more trapezoids. The problem is it becomes very cumbersome to do those calculations. So what we're going to do is we're going to go to our calculators and we're going to open that TNS document that I sent to you, the Riemann sums document. I'm going to teach you how to use it, and we're going to find the LRAM, the RRAM, the MRAM, and the trapezoid values when n is 10, 50, and 100 subintervals. Imagine having to do that by hand. No, thank you. Now remember, if n is 10, that means our base, because we're still going from 0 to 2, is 2 minus 0 over 10 is 1/5. If n is 50, we have 2 minus 0 over 50. Our delta x is 1/25. If n is 100, the length of each subinterval is 1/50th. These are really small intervals. Okay, let's go to the calculator. So here we are in the Riemann sums program. So notice it tells you you'll be able to drag the points to change the values of a, b, and n. Now, I'm going to go to page 1.2. It also tells you that the page is split horizontally into 2 screens. You can change f1 of x by editing the equation. You can change a or b by dragging points. You can change n by dragging the slider in the lower screen. It will give you all of the values for an left RAM, an MRAM, or a right RAM, and I believe it also has the trapezoid in here too when we get here. The T stands for trapezoid. Okay, so here's our function. That's not the function we want, so I'm going to double click on it, and we want to change our function to the backspace. I'm going to make it 2x minus x squared. Click down here, so now we have our graph. Now, we are only concerned from 0 to 10, but notice I want my a to be 0. I want my b to be 2 because we're graphing from 0 to, notice on the bottom here, here's my value of a, here's my value of b. So I'm going to bring this back all the way till the b says 2. Now we can shrink this so we have a better picture. Let's say we go from -2, tab around. Let's make that say a 10, tab over, make that a 5, tab down. We have no negative, so let's just make that a -1. Okay, That looks good. That way we'll have a better picture of what's going on. Maybe we even change this from 5 to only 3. Okay. And let's change this to say a negative 0.5. Just trying to get as much as we can to see what's going on. Okay. Now, right now, n is set to be 1. And it tells us the approximate area. Why am I back in this function x squared plus 2? Let's do this again. Oh, because I clicked and didn't hit enter. That's probably what I did. So 2x minus x squared, make sure you press enter. That's better. We can make this 10. Make that 10 lower. Let's make that a 4. Let's make it even smaller than 4. 2. Oh, let's see. Okay, so that's just so we can get a better view. All right, so now n is 1 here, and it's telling us the area there is 0 because that rectangle has an area of 0. The exact area is 1.333, so 4/3. Notice this area here, the 0 is for an LRAM. If I take this and slide it, the midpoint area approximation, notice the rectangle's been drawn in orange, is 2. And if we go to R, and we go to T for trapezoid. Now, we did where n was 4. So I'm going to take this slider and I'm going to drag, and notice underneath it says n is 4 here. I'm going to drag it and I can see 1, 2, 3, 4 right rectangles. So they got the answer 1.25 for the right. The midpoint, they got the answer 1.375, same as us, right, and trapezoid. Okay, so now we're going to, in our box, we want when n is 10. So we're going to drag this. Whoops. And it's a little tricky. Get your n is 10. 1, 2, 3, 4, 5, 6, 7, 8. That doesn't look like 8. Oh, let me get over here to my L first of all. There's my n is 10. Be careful when you're setting your n's that when you're at 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sometimes it says 10, but there's 11 rectangles. That means you're not exactly on the 10. Okay, so be very careful and make sure that you count those rectangles as best you can. Now, I know that's going to be hard when we get to 100, but we're going to do the best we can here. Okay, so our LRAM is 1.32. Our RRAM for our table is 1.32. Our MRAM is 1.34, and our trapezoid is 1.32. And notice how well they fit. That trapezoid is a pretty good fit, right? Now let's change our n to 50. Look at those rectangles as we make this bigger. Okay, so here we have for n equals 50, our LRAM is 1.333, our RRAM is 1.333, our midpoint is 1.334, and the trapezoid is 1.333. Now we're going to go back. Now let's make our n 100. And we get 1.333. The RRAM is 1.333. The MRAM is 1.333, and the trapezoid is 1.333. But in all 4 cases, notice there's very little overhang or shortage. It's much closer to the actual area, okay? So this is how we use it. Now, there's a reset button here. If we press that, it's going to reset it to the original A and B, which is a problem in ours because we're only out here at 3. So if you make that 10, now you're back in a window where you can go. It's not going to reset the window and it's not going to reset the function. What I do is I never save it. I open up a new document and I don't save it. That way I don't mess up the original setting. Okay, guys? We will use more of this in class. Now let's back to our lesson. So now hopefully you've been able to fill in this table. If not, pause it, complete it. And now I have a question. What do you think the actual area is? Notice how when we got to 100, all of our approximations were 1.333. That's a repeating decimal, which is 4/3 or 1 1/3. You know I prefer the improper fractions now. Now, if the area under the curve is in the interval from A to B, We know how to find the length of each base of the rectangle or the height of the trapezoid. That's our delta x. That's b minus a over n, where n is the number of subintervals, right? Now we're going to expand on this. We're going to use this. What do you notice about the values of the LRAM, the RRAM, and the MRAM, and the trapezoid as the number of subintervals got larger? As the number of subintervals got larger, notice what happened to all of these values. They all converged to the same place. The numbers converge. That means they get closer and closer to the same number. Remember, getting closer and closer to the same number, that sounds familiar. Sounds almost like a limit, doesn't it? Now the LRAM, I want to think about the LRAM. The LRAM is the sum of all our areas, right? We take our base delta x times the function value at each of the x values, where the x values are the left bounds. So we would have to use k from 0 to n minus 1, because n would be the right endpoint, and we don't use the right endpoint in a left rectangular approximation. Okay, and the summation tells us add up all those areas. Now the RRAM, we're going to add up all the areas of the rectangles, and the bases are all delta x, and the heights are the function values at all the x values that are on the right side of each subinterval, which means k is not going to start at 0, it's going to start at 1 and go to n, because n is the rightmost endpoint. Now MRAM is a little bit different. MRAM, we're going to sum up all of, now the way I'm going to write it, I'm going to have the k's go from 1 to n. It's delta x is the base again, times now the height is, we have to find the midpoint, so we have to use x of k minus 1, since I let k start at 1, plus x sub k all over 2. Now, if k started at 0, and we went to n minus 1, then this would be f of x sub k plus x sub k plus 1 over 2 delta x. They're the same thing. It doesn't matter. Now, the exact area that's under the curve, remember we said when we used more and more subintervals, when we let n get big, when we let n get large, the numbers tended to converge. They all head to the same place. Well, that means that the limit, this is the exact area, the limit as n heads to infinity of the summation as k goes from 0 to n minus 1 of f of x sub k delta x. Now remember, that's the limit as n heads to infinity of the LRAM. Is the same as the limit as n heads to infinity of the summation as k goes from 1 to n of f of x sub k delta x. And again, that's the limit as n heads to infinity of your RRAM. And that's the same as the limit as n heads to infinity of the summation of k goes from 1 to n of x sub k minus 1 plus x sub k all over 2, f of, lost my f of, times delta x, okay? And that is your limit as n heads to infinity of your MRAM. And it's also equal to the limit as n heads to infinity of your trapezoid. Now your trapezoid is the sum of these two, so we really, at the average of those two, I really don't want to write that in summation notation. That's okay. We don't need to, all right? But it's really cool that all of those limits are the same. They all head to the same place when you use a tremendous amount of rectangles or trapezoids. Let's do one more problem here. Let's approximate the area under the curve for f of x using the indicated methods. So we're going to do an LRAM sub 5. Now notice there's 1, 2, 3, 4, 5, and it's very nice because each of those changes in the interval has a length of 5. So our LRAM, I can factor out our base, which is 5, and from 0 to 5, 0 is on the left, so we're going to use f of 0, we're going to use f of 5, we're going to use f of 10, we're going to use f of 15, we're going to use f of 20. We are not going to use the 25, which is the rightmost endpoint. So this is 5 times f of 0 is 100, plus 32, plus 69, plus 60, plus 53. So that's going to be 5 times 314, which is 1,570. Now we're going to do an RRAM. So again, the bases are all 5, so I can factor that out. Now we're not going to use the leftmost endpoint 0, but we are going to find f of 5 plus f of 10 plus f of 15 plus f of 20 plus f of 25. And that'll give us 5 times 32 plus 69 plus 60 plus 53 plus 49. And guys, yes, you can, since they gave you a table, start on this line and skip this line. That's also okay. All right. So we have 5, and if we do the addition inside, we're going to get 263. Multiply that by 5, we're going to have 1,315. There we go. All right, now we have a trapezoid to do. So it's nice, all the bases, or actually all the heights this time, because remember our heights are delta x, they're all 5. So our trapezoid is 1/2 times the height 5 times, we're only going to use the 100 and the 49 ones. So f of 0 or 100 plus 2 times the f of 5 plus f of 10 plus f of 15 plus f of 20. Now I'm going to have to close it because I'm done doubling, plus f of 25. So that's 5/2 times f of 0 was 100 plus 2 times 32 plus 69 plus 60 plus 53 plus 49, and then that's 5/2, and we're going to have 149 plus 2 times 214 is 5/2 times 149 plus 428, which is 5/2 times 577. Oh boy, 2,885 over 2, which is 1,442.5. Yay! Oops, I lost my 1 in my box. Okay, so there we go, guys, and there we have it. Make sure if you did not get the program, the TNS document in class today, that you bring your graphing calculator, your personal graphing calculator to school so that I can transfer it into your calculator. Have a wonderful day, guys. Bye.